In the previous class, we were discussing about the computational accuracy in DSP implementation. Okay, here I will discussing about number formats. Where there are two types of the number formats. One is fixed point format, and the other is floating point format. Okay, again we classified the fixed point format as fixed point, integer format, fixed point, fractional format. Okay, here fixed point integer format, we already know that what is the format for that, number format, number representation format. Okay, just remember here s equal to 0 it's positive, s equal to 1 it's negative, and what is the most negative value and what is the most positive value, you can find out within the, like this we can find out the most positive and most negative number. Then the range of the integer range, that is equal to minus 2 raised to n minus 1, this one. Okay, less than equal to x is less than greater than equal to minus 2 raised to n minus 1, and less than equal to 2 raised to n minus 1 minus 1. Okay, then we gone through this problem also, and how we can convert it. Okay, here if it is minus 2 means what is 2 here? 2 is 1 0, right? Okay, that's why minus means here we know that s equal to 1 it's a negative number. That's why minus 1 into 2 raised to 2 plus 2 is 1 0. That's why 1 into 2 raised to 1 plus 0 into 2 raised to 2. Similarly, okay, that is, and then fractional format is the representation, number representation. Okay, the most negative value is minus 1 and the most positive value is minus 1 minus 2 raised to minus n minus 1. Okay, this value. Okay, go through the number representation here, and just go through this problem. Next here, one more integer, one more format is number of representation format is floating point format. One is already discussed, fixed point. Fixed point in that fixed point integer, fixed point fractional. Now floating point format. Okay, this floating point format suitable for computation where a large number of bits would be required to store immediate and final results. Okay, here for example, algorithm involve summation of a large number of products, multiplier or accumulator. Okay, here the floating point number x is represented as x equal to mx 2 raised to ex. Here mx is called as mantissa and ex is called as the exponent. What do you call it as? It's as exponent. This one. Just remember, mx is mantissa and ex is exponent. Here in floating point format, when you are doing the multiplication, for example, the product of two floating point numbers, if x is equal to mx 2 raised to ex and y is equal to my 2 raised to ey, then xy is equal to, then what will happen here? Mx and my, these are the mantissa, both are multiplied, then 2 raised to ex into 2 raised to ey. What will happen? 2 raised to ex plus ey it becomes. Then a floating point number, a floating point multiplier must contain a multiplier for the mantissa and an adder for the exponent. Just remember here, for the mantissa, multiplier for mantissa and adder for exponent, adder sign here. Okay, then a floating point adder requires normalization of the numbers to be added so that they have the same exponent. For example, 4 into 10 raised to 6 plus 2 into 10 raised to 3. Then what we can do here? Is it possible to add? No. Why? Why it's not possible? Here we have the 10 raised to 6. Here we have the 10 raised to 3. What we can do here? We can make 10 raised to 6 in terms of 10 raised to 3 or in terms of 10 raised to 6. See here, it did x plus y is equal to mx 2 raised to ex plus my 2 raised to ey. Okay, then what he did here? Mx 2 raised to ex minus es, sorry, ey, mx into 2 raised to ex minus es, again multiply it 2 raised to es plus my 2 raised to ey minus es 2 raised to es. Then what will happen here? The 2 raised to es is common. I will take 2 raised to es as common. Then mx 2 raised to ex minus es plus my 2 raised to ey minus es. Here, this both are same. Then we get the addition value. Okay. Here we can make the. It's not possible to do the multiplication. It's not possible to do the multiplication of this one. Then what we can do here? We can make this exponent values, okay, same. Exponent values same. Then we can perform the addition, floating point addition. Okay. Okay, just remember this. Then a commonly used single precision floating point representation is IEEE 754 1985 format. What is that? Just remember, x is equal to minus 1 raised to s into 2 raised to e minus bias multiplied with 1 plus s. Multiplied with 1 plus s. Where s is sign bit, e is exponent bit, f is fractional bit. That means we call it as significant. Significant. See here, if you consider for the 32 bit, in that first bit is sign bit and 8 bit for exponents. Okay, the after exponent here the dot decimal point, that means implied binary point. After that 23 bits are fractional bits, or we call it as significant. Okay, here a commonly used single precision floating point representation is IEEE in this format, IEEE 754 1985. Okay, this is the serial number when it registered under IEEE, and this is the year. Okay, just remember x is equal to minus 1 raised to s multiplied with 2 into e raised to minus bias into 1 plus f. Okay, f is the magnitude fraction of the mantissa. Magnitude fraction of the mantissa. Where, note, in determining the full mantissa value, a 1 is placed immediately before the implied binary point. Later we'll discuss some problem, then we will get it. Okay, then e is the bias exponent. Here the bias makes sure that the exponent is signed to represent both small and larger numbers. The bias is set to 127. Means here largest positive number represented by 8 minus 1 bits. That means 2 raised to 7. It is 8 bit means, okay, 8 bits are reserved for exponent. Okay, that's why 8 minus 1 is 7, 2 raised to 7. That means the bias is set to 127. Then s gives the sign of the fractional part of the number. If it is 1, it's positive. If it is 0, it's negative. Okay, then find the decimal equivalent of the floating point binary number with bias 2 raised to 3 minus 1. So here I will show the problem here. Here in your textbook they given in the place of, see here, 1 plus f, 1 plus f is there, but in textbook it's 1 dot f. That's why you can make it changes. Okay, in front of in terms of instead of plus you can put multiplication sign. Okay, just make the changes here. 1 dot f. Okay, here they given one problem here. S. Find the decimal equivalent of the floating point binary number 1011 4 zeros 3 ones 0 0. Assume a format similar to IEEE 754 in which the MSB is the sign bit followed by 4 exponent bits followed by 8 bits for the fractional part. Just remember here. Okay, this one bit, this bit is for sign bit. Then these 4 bits reserved for exponent, and here the dot will come. Then it's a significant. That means F 1 E F. See here. Yes, E F. If it is 1 means which value is? It's positive or negative value? If it is 1 means it's a negative value. See here, I think they given same problem here. Yes, I think they given same problem here. Okay, S equal to, sorry, S equal to 1. Okay, exponent for exponent 4 values. For significant, the remaining values. How many values in problem they given here? 4 exponents and 8 bits for fractional part. That means F is equal to 8. 1, these 4 bits for E, the remaining bits for significance. Here, one is sign, biased exponent, and significant. Here the dot will come. In here, the decimal point. Here, implied binary point. Implied binary point. Here, after the binary point, whatever the value is given, when we are converting to the decimal value, 0 into 2 raised to minus 1, 0 into plus 0 into 2 raised to minus 2, plus 0 into 2 raised to minus 3, plus 1 into 2 raised to minus 4. See here, this one, this part. Okay, it becomes 0.109375. Just remember this. Okay, then exponent value. That means behind this one. Behind this one means 0 into 2 raised to 0 plus 1 into 2 raised to 1 plus 1 into 2 raised to 2 plus 0 into 2 raised to 3. Here. 0 into 2 raised to 3 plus 1 into 2 raised to 2 plus 1 into 2 raised to 1 plus 0 into 2 raised to 0. That is 6. Okay. Then here x is equal to, in this format we can write it. Okay. X equal to minus 1. Which sign here? 1 means the most significant bit is 1 means it's negative value, right? That's why written minus 1. Then here, in determining the full multiplier value, a 1 is placed immediately before the implied binary point. See here. Just remember this. That's why 1 point. What is the f value? See here. This is multiplication dot only. Okay, change it. 1 dot. Okay, 1 dot. What is the f value? 109375. 109375. Multiplied with, okay, 2 raised to, what is the e value? E value is 6. 6. Yeah, okay. E value is 6 here. We already calculated. Minus, okay, bias value. The bias value means it's 7. Always remember the 8 minus 1 bits. Bias value is 7. Bias value is always, it is 7. Just remember it. Okay, that's why 6 minus 7. After substituting all the values, you will get minus 0.5546875 here. Yeah, same problem here. Okay, minus 0.5546875. Just remember this. It's very important. Okay, this problem. Okay, go through this one. It's very important. Okay, then here, what is the disadvantage of floating point over the fixed point? Here the speed reduction. That is the most disadvantages of the floating point representation. The floating point multiplication requires addition of exponents and multiplication of the magnitude. And also floating point addition requires exponents to be normalized. That means here we can make the changes in the exponent value. That means here in addition you can make the uh, exponents equal. Then only the addition is possible. That is about this. There are the disadvantages. Okay, when we consider about the speed. Then dynamic range. What is the dynamic range? Here, the dynamic range, the ratio of the maximum value to the minimum non-zero value that the signal can take in a given number representation scheme. That is called as dynamic range. Ratio of the maximum value to the minimum non-zero value that the signal can take in a given number representation scheme. Okay, where uh, this is the number represent integer number representation, 6 point. X is equal to minus s to the n minus 1 plus b of n minus 2 to the n minus 2 plus b of n minus 2 to the n minus 3 and so on. Okay, the dynamic range is proportional to the number of bits n used to represent it. Just remember this. Okay, for example, n is equal to 24. Okay, just find out the value. 24 means minus for integer value. Okay, integer range is minus 2 to the n minus 1 to 2 to the n minus 1 minus of 1. See here in first page, first we have to discuss. Yeah, this one. Minus 2 to the n minus 1 to 2 to the n minus 1 minus 1. That one. Okay. Here after substituting, we'll get the value minus 8 lakh 8 lakh. Sorry, 83 lakh 88,608 minus here 83 lakh 88,607. Okay, x belongs to, this is the negative value, this is the most positive value. Okay, we always going to take the x minimum value. This minimum value non-zero minimum value is 1. Okay, minimum non-zero value is always is 1. Just remember. Then x max is equal to, okay, 83 lakh 88,608 divided by 1. This is, we'll get this one. Okay, then you can find the, in terms of dB, you can decibels. You can represent the dynamic range. 20 log of 83 lakh 88,608. Then you will get the dynamic range is 138. Similarly for floating point representation. Okay, here how we can calculate the dynamic range for the floating point number. Here already we discussed that 15-bit significant f, 8-bit exponents, and 1 bit for the s. Then the bias is already we know that it's 128. Okay, then here in the computation of dynamic range, f is conveniently set to 0 and the sign bit s is irrelevant due to absolute value. Then here x is equal to minus 1 raised to s into 2 into e raised to minus bias into 1 plus f, means here you can set to 0. A computation of dynamic range can set the f value to 0. Okay, then here minus 1 raised to 0 into s is also set to 0. S and f both are set to 0. Okay, then here it becomes e value. Let me e value is 1 into 2 raised to 2 times 8 minus 1, 127 minus of by s. Okay, x minimum value is 1 into 2 raised to 0 minus by s. Okay, the highest value is negative minimum value. This is the value. It's equal to 153535 dB. We get it. Okay, but here in your textbook they given the dynamic range of a signal is the ratio of maximum value to the minimum value that the signal can take in the given number representation scheme. Okay, but here it's audible. In textbook they given here how we can calculate the dynamic range. The dynamic range of a signal, okay, there is no equations like this. There is no equations like this. Directly we can find out the dynamic range by the total number of the numbers. Okay, the dynamic range of a signal is proportional to the number of bits used to represent it and increases by always 6 dB for every additional bit used for the representation. Okay, what are the number of bits? What are the number of bits used to represent? That value is multiplied with 6 dB. Directly we get the what dynamic range. Instead of using this equation, you can practice this also. Otherwise, directly how many bits here? 24 bits. 24 bit is multiplied with 6 dB. Then here we will get the dynamic range 144 dB. This one is here. This is very important. The dynamic range of a signal is proportional to the number of bits used to represent it and increases by 6 dB. What are the number of number of bits used to represent it? Not only that, for that value we can multiply it. For example, here 24 bit means 24 into 6 dB. That becomes 144 dB. Similarly, B 48 bit here, 48 into 6 dB to 88 dB. If it is the third one, a floating point format with 16 bit mantissa and an 8 bit exponent. Okay, in this case, okay, we discard you can make f equal to 0. F and s equal to 0. They mentioned here. F0, S0. Same thing he did here. S0. Then how we can find out? Here 2 raised to 8. How many bits here? He used 8 bit for exponent. That's why 2 raised to 8 minus 1 multiplied with 6. If it is 7, 2 raised to 7 minus 1. If it is 10, 2 raised to 10 minus 1. How many number of the bits are used for exponent? That value 2 raised to 8 minus 1. 2 raised to 8 minus 1 into 6. That means 255 into 6 dB. That is 1530 dB. Same value will get here. 1.35 dB. Here 1.30 dB. See here. Okay. Then here next one is resolution. Resolution is the minimum value that can be represented using a number representation format. Resolution is the minimum value that can be represented using a number representation format. For instance, if n bits are used to represent a number from 0 to 1, the smallest value it can take is the resolution. The smallest value it can take is the resolution. What is the equation? Which equation we can use it? Resolution is equal to 1 divided by 2 raised to n. Just remember this one. Okay. The resolution of a number representation format is normally expressed as number of bits used in representation. At times it is also expressed as a percentage. Resolution which can be determined in terms of the percentage. That's why just remember this is the equation for to determine the resolution. See here, how many bits here? 24 bits. 1 divided by 2 raised to 24. Okay, it's in terms of percentage. That's why multiplied with 100. Here the 48 bits. That's why 1 divided by 2 raised to 48 into 100. Okay, then here this one, the resolution, to get the resolution here, how many bits are used here? For 16-bit matrix. Here you can consider the matrix value when calculating the resolution. That's why 1 divided by 2 raised to 16 into 100 multiplied, that is equal to 1.5 into 10 raised to minus 3%. Just remember here, this is just refer the table here. Okay, here how he did, he used some different equation. 1 divided by 2 raised to k minus 1. Simple here, n is equal to 24 means 2 raised to minus 23 into 100. That means 1.2 into 10 raised to minus 5%. Here we'll get some different values. Okay, better we go for sorry, shit. Better we go for your subject notes only. This one only. Okay, just remember this one. This is very easy. Resolution equal to 1 divided by 2 raised to n. Then what about the precision? Precision is an issue related to the speed of DSP implementation. In general, techniques to improve the precision of implementation reduce its speed. Larger word size improve the precision, but may impose a problem with the speed of processor, especially if its bus width is also limited. For example, the 32-bit product of a 16 cross 16 multiplication has to be preserved without loss of precision. Two memory access are required to store and recall this product using a 16-bit bus. Another example is the rounding off, as against the truncation used to limit the word size in the fixed point representation of the number. Okay, this is about the precision. Okay, just go through this problem here. Just go through the problem. Okay, this completes the second chapter in the first module. Okay, one more is here, double precision fixed point format. It's not covered in the regular class. Okay, double precision means the fixed point format, integer format means, for example, it's 24 means. Double means here you can double it. That means it becomes 48. To increase the range of numbers that can be represented in fixed point format, one obvious approach is to increase its size. The size is doubled, the range of numbers increases continuously. Okay, simply doubling the size and still using the fixed point format creates what is known as the double precision fixed point format. Okay, just remember the double precision fixed point format, again double the range, double the number of bits used for representation. Okay, if you double the range bits also, what about the range also double. Okay, this is about the double precision fixed point format. Okay, this completes your module number 1. Okay, do you have any doubts? Please go through this chapter 2 is also very important. Okay, go through that problem. Okay, and fixed point format. In fixed point format, integer and floating point, sorry, fractional number representation. Okay, then in floating point number, just go to the representation of that one, which consists of mantissa and exponent. Okay, how we can do convert it to the decimal value? Okay, just remember that remember the IEEE that format. Okay, and one more important is dynamic range. How we can calculate the dynamic range and resolution value? That is also very important. Okay, refer that problem here. Better you can refer the textbook. Okay, thank you.